Good morning, guys, and welcome back again to Algebra 1 today. As you may have noticed, that I am out of the building. Today, me and a couple of the other math teachers are taking some students up to a math day field trip at CSU Fort Collins. So we're out for the day. We'll be back on Friday. In the meantime, you have a video lesson today diving into the work behind solving equations, where sometimes you get the algebraic approach, sometimes equations that are literal equations. So we've been kind of building up this skill for a while now. The last skill that we were focusing on in our last lesson was this idea of like structurally thinking about how to like organize the steps and trying to solve for a variable in an equation. Sort of justifying the process as behind what is it that we're doing and why we're doing it, right? We're going to continue to do that today as we get our CFAs back. We work through some CFA feedback. And as we dive a little bit further into solving literal equations in particular, where instead of constants, you got variables everywhere. So as we get into it for today, please make sure to bring your phones on up to the wooden caddy in the correct number slot assignment. Just like we usually do at the beginning of class every day, we'll have phones away for class while we're working. In the meantime, the sub is going to have copies of your CFA assessment that they're going to pass back to you. Your CFA is going to be grouped in with a particular page of a practice assignment that I came up with to kind of help push you guys in the right direction. So please be sure that in your CFA, when you get it back, you're overlooking the feedback that you've got and that you're working through some of the feedback practice in just a moment after we get out of our initial warm up. So before we launch into it, what I want to do real quick is get the gears turning with a couple of retrieval problems from pages 25 and 26 in our notes proper. You'll notice over here on the right that we're going to solve the equation shown below. We got variables on both sides. That can be sometimes a little tricky to think about, but we'll walk through the process behind how we're going to solve that here in just a minute. The other one that you'll notice over here on the left-hand side is instead of equations, you got some inequalities. And what they're asking us to do is to do an operation to both sides of the inequality to see if it's still true. And this is eventually going to lead in the direction that we're working in as we go into the second half of the unit, once we wrap up with the first part of the summative coming up next week. So pause the video, take a moment. I want you to manipulate those inequalities on the left. When you perform those operations on both sides, do you still have something that's true? The thing on the right-hand side, what I want you to think about is how you might be able to solve that. Some students are going to feel super comfortable with this. Some of you guys might be looking at this and kind of wondering where's the first place to begin. So give it your best shot. In just a moment, so here we'll bring it back in and kind of discuss. All right. So for the left-hand side of the board, what we've got are some inequalities. This first one is that 7 is greater than -3. If you think about inequalities, oftentimes one sort of visual that you see a lot with these is the real number line. The real number line usually has 0 in the middle, and then all the negatives are to the left of it, all the positives are to the right of it. It includes all of our friends. We got fractions, whole numbers, integers, rationals, irrationals, all the numbers that we're aware of can be found somewhere on this number line on either side of 0. If I take a look at this and I say, hey, is 7, say, greater than -3? What you'll notice is because 7 is to the right of -3, that checks out and is a true statement. No real surprises there, though, right? I think a lot of us can kind of look at that and inspect it and say, yeah, that should really be true. What we're going to do, though, is we're going to add 5 to both sides of that inequality and see if that's still true now that we're sort of changing it and modifying it. So as I'm working here, if I look at 7 plus 5, I'm going to notice that makes 12. If I do -3 plus 5, that's going to give me +2. So if I think about the number line now, it's kind of like I'm taking all the old endpoints that I was working with and I'm moving them over 5 units. So if I had a point at -3, he's gone right 5 units to 2. And this point over here for 7 has gone right 5 units, 8, 9, 10, 11, 12, over there to +12. Now, if I think about which one of these is larger than the other, 12 is larger than 2, so the inequality is still the same. There's no difference in the truth value of this. All we've really done is we've gone and we sort of translated these coordinates, right, off to the right 5 units in either direction. So should still be true, right? That seems feasible. If I think about another one where I've got, say, -8 is less than 12, that's a true statement. A negative number is definitely less than a positive number. It's further to the left on the number line. What we're going to do though is we're going to sort of double it, and we're going to see if that still proves to be true. Now, what's going to get interesting here is if I double -8, that's suddenly going to become something like -16, so it's even further off to the left. If I take 12 times 2, that's going to become 24. That's even further off to the right. But the number on the right is still to the right of the number on the left. So the inequality still hasn't changed, right? It's maintained its truth value here. And if you wanted to kind of sketch a diagram for this, what you could do is draw a real number line where you got 0 smack dab in the middle. You could start with like -8 on the left. You could start with 12 over here on the right. And if you're doubling it, you're kind of like taking that distance away from 0 in either direction, and you're going that same distance again in either direction further away. So -16 over here is twice as far away from 0 as -8. 24 is twice as far away from 0 as 12. But 24 is still larger than -16. It's still further to the right, so no changes there, right? Now, if I take a look at this last one, where I've got 6 is less than 10, that's a true statement, right? 6 is in fact less than 10 on the real number line because it's further to the left. So if I sketch that diagram here, what I'll see is that I've got 0, and then I've got 6, and then I've got 10. 6 is left of 10, so that's good. But now we're going to do kind of this last operation where I divide both sides by -2. And where I've got to be careful here is that when I divide or multiply by a negative, the sign of my original number needs to flip to compensate, right? So 6 divided by 2 would be 3, but 6 divided by -2 is now -3. And similarly for 10, 10 divided by 2 is 5, but 10 divided by -2 is -5. If I think about whether this inequality is still true, you get something kind of interesting. If you look at the real number line and you think about where -5 and -3 are, -3 is to the right of -5. So -3 should be greater than -5. And we've encountered kind of our first problem, right? If I multiply or divide by a negative number with an inequality, one thing that I'm going to notice is that it's actually the other way around. I'm going to have to take the inequality, and I'm going to have to flip the direction in which it's facing. So I can no longer say that -3 is less than -5. I've got to be a little more careful than that, right? I've got to say that now -3 is greater than -5. And again, this is kind of feeling probably a little bit out of left field. It's going to be more useful as we go into some of our next sequences of lessons. So we're going to start to slowly kind of weave this inequality work in as we go a little further in the material. So as a heads up, we're going to see some more of that. Now, returning into a little bit more familiar territory, if I'm looking at how to like solve an equation, right? 3x plus 6 equals x plus 14. I noticed that this is one type of problem that some people had a harder time on the CFA with. It was also one that maybe was a little trickier from the work that we were doing in our last lesson. Generally speaking, we know that to solve an equation, we have to undo things. And our goal is usually to try and get x completely back to being by itself. What makes this type of setup a little strange compared to the others is that there's not just a single x anymore, right? There's x's on both sides of the equal sign, and I've got to think about what to do in that situation, right? Some people, I think, have a hard time visualizing like what a solution to that might look like. So what I want to introduce here is kind of like a picture-based way of making the argument, something called a hanger diagram. And this is more like a visual way to kind of ration through the different steps of the process and trying to arrive at an answer without necessarily taking a lot of algebraic steps, at least not at first glance. Now, what on earth is a hanger diagram? Imagine that you have a hanger hanging from the ceiling, and in an equation, you want it to be perfectly balanced, right? You might have a disproportionate number of terms on one side or the other, but their weights are going to keep it balanced. It's going to be perfectly equal. Now, in order to assemble the hanger diagram, what I'm going to want to do is represent my variables and represent my constants. I've got 3 unknown x's on the left-hand side of my diagram, and then I've got 6 like blocks, you can think of it, alongside that side there. And each of those blocks is like 1. So you can imagine there's like x, x, and x, and then there's 1, 1, 1, 1, 1, 1. On the right-hand side, I've got one block for X, and then I've got like 14 uh, of these other little guys going on, and it's like a perfect balance so far, right? Now, I want you to kind of think through this by like the process of elimination. If this is a perfect balance between the two things, which of these objects are in correspondence with the other? Well, if you think about the little like 1 unit blocks on either side, I've got like 14 of them stacked up on the right here. It's kind of hard to draw 14 little blocks. I've got 6 of them over here on the left. If there's a perfect balance between these two branches of the diagram, that must mean that 6 of these little unit blocks are going to correspond over here to like 6 of these little unit blocks, right? So those are balancing each other out perfectly. And I can more or less ignore them if I'm trying to figure out the mysterious value of X, right? Now, if I ignore them, that means the 6 unit blocks on the left are no longer really part of my thinking, right? But over here, if I have 14 of them and I'm removing 6, that's ultimately going to leave me with 8 left. Now, I'm going to do sort of similar thinking here with like one of the blocks for X. I've got a 1X block on the right, and I've got 1 over here on the left. Those are in perfect balance. So they're kind of corresponding and canceling each other out. Now, what I want you to think about what you're left with here is that you've got 2X blocks and you've got 8 unit blocks on the right-hand side. There's a perfect balance between them, right? So how many unit blocks must each of the X blocks weigh? Well, if there's 2 of them and they have to balance out with 8, that would tell me that each of those X blocks is ultimately weighing like 4 ones, 4 unit blocks, so to speak. So my solution to this is going to look like X equals 4. I want to kind of point out how that's an analogy to what's going on algebraically if I were to think about how to solve this equation. Notice that if you start with like the unit blocks on both sides, you have plus 6 on the left-hand side, and you've got plus 14 on the right. How could you move that plus 6 or cancel it out? Well, the opposite of that would be like minus 6, right? But you've got to do it to both sides of the diagram or both sides of the equality to get it to balance, right? So if I cancel out that term, what that's going to leave me with is that I've got 3x is equal to x plus 8, which is where we were at in the next stage of the diagram drawing, right? And similarly, if I think about like the x block, one of those x blocks on the right is going to cancel with one of the x blocks on the left. So after I subtract the x block from each side to remove it from the diagram and remove it from place, so to speak, now I've got 2x is equal to 8. So what that's left to tell me is that I've got 2 of these x blocks, and they got to correspond to 8 unit blocks, which means each of those x blocks has to correspond to 4 units. And the reason I got that answer is that the last thing I've got to do is just divide those 8 blocks into 2 groups. And I saw that x was equal to 4. So there's a lot of different ways to kind of reason through the solution process for these equations. The idea of like inverse operations and like opposite steps being performed on X is really useful in most cases, but it's maybe not so useful in scenarios where you got variables on both sides, right? I think some people are maybe having a hard time imagining that or picturing what to do. So if you find yourself in one of those situations, you might find like one of these hanger diagram setups a little helpful. If you think about like maintaining a balance, you can kind of pair things off in the picture and go, yep, that's balancing with that, that's balancing with that, and then whatever's left over is really what you're focusing on. You can kind of reduce the problem down to something that's maybe a little more approachable. I'd never really seen one of these before. I had another teacher in the math department like draw this out for me and show me how to use this to think, and it made a lot of sense to me. So I wanted to kind of share it with you guys to make sure that you have it as like an extra tool in the tool belt. But yeah, as we go into kind of the next phase of our class for today, what I want you to do is look over your CFA assessments and see how you're doing so far with the process of solving equations. Generally speaking, I think we're off to a really good start. especially the idea of like what's happening to X and what we're doing to undo it later. What I want to make sure we do is take a little bit of time to continue kind of practicing that before we dive a little too far into literal equations. I want to kind of spend one last little chunk of time here while you're with the sub, focusing on algebraic equations, solving for X. We're getting a definite number across a variety of different setups. So you should have your CFA passed back to you. You should also receive like a personalized practice sheet. There's like three groups of types of problems that I came up with. I noticed a lot of people in 1A were either in kind of one group or another, where they're practicing just different skills with solving equations. Not necessarily like one is harder or easier than the other, so much as they're just kind of like different setups. So pause the video. I want you to take maybe about like 10 or so minutes to try and find some solutions for each of those different cases. At the end of 10 minutes, what we'll do is we'll sort of bring it back in and discuss through maybe a couple of the examples, and then we'll finish up the notes for today and talk a little bit more about some of the new stuff with literal equations. All right. So you guys have had maybe like 8 or 10 minutes to kind of mull it over yourselves. You'll notice that you're either in set one or in set three, at least if you're in my A-Day students for this video. Set one and set three, I wouldn't necessarily say one is easier or harder than the other, so much as like the layout and the strategy is a little bit different in each one. You'll notice in the first setup that I've got this like kind of table on the right-hand side of the problem, where I'm distinguishing between like what's happening to X versus what I'm doing to solve for X, right? And what I'm trying to get at here is like the logical process, the steps that we take and when we take them to try and get X back to being by itself and finding a solution. Now, here's what I mean by what's happening to X. And I'll try and color code this that I'm thinking like in terms of like the blue setup, which is one process, and then I'll show the reverse setup we're solving where we're doing it in red. So first, there's some unknown quantity X. If I'm looking at the left-hand side of the problem here, I notice that two things happen to it. First, there's X, and then X is multiplied by -4 to become -4x. Once I have -4x, finally, I add 7 to it to set up the equation. What I want you to notice here is that there's an order to this process, right? First there's x, and then I multiply by -4, and then I add 7 to create this mess. And I'm trying to solve it, right? I'm trying to eventually work it backwards so that I can make a determination about what the final solution is. Now, if you're running this backwards to solve, what you have to bear in mind is that you got to go backwards through the process and you got to do the opposite of what you had originally done in the first place. So what I might do here is kind of run this backwards, where instead of going 1, 2, 3, I'm going to go like 3, 2, 1 in the rightmost column. Now, the last thing I did creating this expression was that I added 7. So the first thing I'm going to do when solving is subtract 7. My next step after I do that is to try and undo multiplying by -4, which means that in this context, I'm going to divide by -4. And then I'm going to finally have X, and I'm going to know what the solution is. So you'll notice here in red that I'm going backwards and I'm undoing whatever it was that I was going in the forward process with blue to create that compound expression on the left-hand side of the equality. So let's run the steps and see what it looks like, right? Here, my first move is that I need to subtract a 7 from both sides. So what I'm left with is -4x is equal to +4. Then I need to divide both sides by -4. And what that's going to give me is a final answer that x is equal to -1. So I solved my equation. Now, if I wanted to check that that actually is the solution, what I can do is plug it back in and see if I get the same thing on both sides. So if I do -4 times -1 plus 7, if that really does equal 11, I know I'm good to go. -4 times -1 is 4. 4 plus 7 really is 11, so it checks out. My math is good, and I know I found the solution. There's a way to verify these things. Once you've seen that, if you're working into this particular group, definitely make sure you try those next two. They're also examples of two-step equations. One of them's got a fraction though. That one can be a bit of a doozy, and we'll kind of review this once I'm back in class. Otherwise, I think the other type of group that I saw a lot of people having a hard time with was this approach with variables on both sides of the problem, right? With variables on both sides of the problem, you can think in terms of like that hanger diagram. That's a really nice way to do it. But sometimes, like this guy, you'll notice that there's a little bit of a complicating factor. Sometimes you got to kind of worry about like other things in the way first, like this distribution scenario that we got to sort of figure out. So one thing that I often tell my students is that in the process of solving an equation, sometimes you got to simplify it first. You got to kind of clean it up and condense like terms and just make it a little easier to work later. If I see a 3 outside of parentheses and I want to think distribution, bear in mind what math operations happening there. What I'm really doing in that setup is I'm multiplying onto each of those terms as I bring them back together. So I'm going to do 3 times 2x, that's 6x is the first term. I'm going to do 3 times 6, that's plus 18 on the second term. And now I'm back in business, right? Now I've got this set up again, where I'm able to try and think about some solutions. One thing that's kind of tricky about this one is if you're thinking in terms of a hanger diagram, you got some terms that are negative, and you got some terms that are positive, right? If you're thinking about positive versus negative terms, and you're thinking about like how to hang them in the hanging diagram with their negative, that can sometimes be a little bit of a doozy. The hanger diagram might be a little bit easier for like this bottom leftmost problem. So I might try and approach it maybe by a different angle here. Now, one thing you'll notice is that in setting up that hanger diagram and then switching to an algebraic process, we noticed that we needed to balance the equation by doing one thing to both sides at the same time. What you may have noticed is that we're moving constants to one side and we're moving variables to the other. I'm going to take a look at this left-hand side and notice that I have like a negative 14. If I want to move that guy over, then the opposite of losing 14 on that side is going to be to add it. But I've got to add it to both to maintain the balance, right? So that's going to take me to my next step, where I've got negative 2x is equal to 6x plus, I think that's going to be 32, if memory serves. My mental math sometimes is not spot on, but I think that's about it. Now, in this type of approach, if you move the constants to one side, you're going to have to take the variables and move them off to the other. So if I move my constants to the right-hand side, I want to move my variables off to the left. So if I've got 6x on the right, I've got to subtract that away from both sides of the equation. And where that's going to take me is that now I've got negative 8x is equal to 32. So from here, what I'm going to notice is that my final move is to try and divide both sides by negative 8. If I do a positive number divided by a negative number, I should have a negative result. And I see that 8 goes into 32 3 times. So my final answer there should be negative 3. If I want to verify, what I can then do is plug that back into the equation for x, and I can check my work, right? I can sort of simplify it down and see if I get really the same thing on both sides. So if it's balanced, right? If it shows up that it's balanced in the equation, I know I'm good to go. So with that, I wanted to make sure that we spent just a little bit of time kind of reviewing some of the findings that we see from our CFA to kind of continue supporting you guys as we're building up this larger skill of solving, right? This is not necessarily an intuitive process. Some people, I think it's just clicking and they're like, yep, I got it. And for some people, it takes a few times to really kind of see the flow behind it and get comfortable with the process. As we go into our stuff for today, we are going to plan to take part 1 of our summative on November the 17th or the 18th. We are approaching the end of the semester rather quickly. We're going to have Thanksgiving break, not next week, but the week after. After we come back from Thanksgiving break, we've only got 2 weeks before we're taking final exams, and then we're out of here for winter break. So this will be our last summative cycle as we're getting ready to close things up for the semester and post some final grades after the final. Today, we are going to focus on solving equations. We're going to continue developing and solidifying this skill of sort of interpreting the structure and what to do and when to do it. But we're going to do it across 2 different contexts. Sometimes it'll be algebraic equations, and sometimes it'll be literal. Regardless of the scenario that we're in, what we saw on day 1 of solving with literal equations is that really the process is no different than what we would see here for, say, regular old algebraic equations. Our goal is to try and undo the equation and get one variable isolated by itself and equal to everything else. The only difference between an algebraic equation and a literal equation is that sometimes with a literal equation, you won't know what the terms are, so you can't really condense them together. So in either case, you might follow the same sequence of steps. You just might notice that you'll never really know for sure what the number is, unless someone tells you, for example, on this problem, what Q, T, M, and B are. They're all different numbers, but I have no idea what they are until someone tells me. That's really common in like the sciences, and economics, anything that's going to have like a formula that you're using, especially in geometry, you'll see that happen. So it's not uncommon to be kind of caught in that scenario. Now, as we switch gears into our notes for today on page 23, you'll notice that there are 8 equations that we're going to be working through. You might notice something about some of the equations compared to the others. To kind of ground out before we get moving today, I want to think a little more strategically, kind of from 30,000 feet at first, and then really get up to our elbows here and try and solve some of these, maybe some of the more tricky ones. As you're looking at this, what I want you and your table mates to think about real quick is what do you notice about the structure of some of these equations? What are some of the things you notice are going on to some of the values or variable expressions in these equations? What do you notice about, say, the number of variables that you see? Which problems might you need, say, the distributive property for? Or which one of these would you say contain fractions? So as we're working through and kind of anticipating our strategies, what I want you to think about is just some initial observations for the equations. What do you see or observe about them? What do you think that's going to mean for you if you're trying to solve them out on the next step? All right, so we got 8 equations. Our goal is to try and solve all of them, I believe, for x. So the goal is the same across the board. One thing that I noticed almost immediately while taking a look at some of these equations is that everything on the left is an algebraic equation where I'm going to get a numerical answer for x. Everything on the right, though, is a literal equation in the sense that there are some numbers at play, but there's not just one variable, right? There's actually two. There's x and there's y. And we're not really used to having y flying around unless we're doing like a graph, right? So that might feel a little weird at first. Something else that I'm noticing is that as I'm making some observations about the structure of the problem, I'm going to see problems 5, 7, 6, and 8. Each of those might need me to use the distributive property before I get to the next step in solving, right? That 2/5 on x plus 3, the 2 on 3x plus 4, I might need to multiply those on there before I can go any further, right? Something else that I'm noticing is that pretty much all of these problems involve a fraction. Problem number 5 is going to involve multiplying a fraction onto x and plus 3, but problems 1 and 2 involve getting two terms divided by 5. Problems 3 and 4 have a term divided by 3. So there are fractions there, but kind of the structure of those fractions is also a little bit different, which might mean that I take some different steps if I'm trying to figure out how to solve them out, right? So I've got to be kind of careful here, right? And all I'm really thinking about are just some potential pitfalls or traps that I've got to avoid, some mistakes that I'm trying to anticipate making, right? Before I actually make them further on in the process. So this is really just meant to give us a moment to kind of digest before we really dig into the process of solving. I want you to take like maybe 15 minutes with your table mates. I want you to try and solve these 8 equations. For all the problems on the left-hand side, what I want you to think about is, okay, how do you get x alone? What's your process? What do you do first? What do you do next? What do you do last? And what's the inverse operation that you're using? For all the equations on the right, what I want you to think about is how is the structure similar, but also a little different? And in the way that the structure of the equation is similar to the structure on the left, what are the steps that you could take to try and get x by itself, even if you don't know what y is yet? So I'll cut you loose here. I want you to take me about 15 or so minutes and give it a spin. Try solving, and we'll bring it back together and discuss and think about what's going on here, and then we'll get ready to move on from there. All right. So as we're moving into the process of solving equations, problems 1, 3, 5, and 7, they're all going to have exact numerical answers. We're going to be able to say exactly what the value of x is. Problems 2, 4, 6, and 8, though, we won't be able to do the same. At least not yet, anyway, right? Now, one thing that I like to think about as I'm thinking about solving equations is what's happening to x and what it is that I'm trying to undo as I'm solving for x, right? So some people refer to this as like a do-undo table. You can think of the do table as thinking first like there was x, and then as I'm looking at what's going on over here on the right-hand side, I'm just listing out the sequence of things that I did to x to get that complicated looking expression. So first there's x, and then I multiplied that by 3. And then I took that 3x and I added 2 to it. And then once I had all that, I took 3x plus 2 and I divided it by 5. That's going to help me make some determinations about what it is that I'm doing if I'm trying to undo or solve the equation. Now, in step 4, I divided by 5. That means in step 1, I probably need to multiply everything by 5 to undo that. If I look at step 3 in the do column, I added 2, so in the undo column, I probably need to undo that and do subtraction by 2. In step 2 of the do column, I multiplied by 3. That means in step 3 of the undo column, I'm going to need to do its opposite and divide everything by 3. And that's going to give me a sequence of steps to follow, so that when I do it to both sides of the equation, I'm going to be able to find a solution and then verify it from there if necessary. So that's what I'm going to do. I'm going to start by multiplying both sides by 5. Notice that 5 divided by 5, that cancels out, right? Those are opposite operations. So I'm left with 3x plus 2. 7 times 5 is 35. So now I'm kind of left at this stage, right, where I've got 3x plus 2 is equal to 35. Now, if 3x plus 2 is equal to 35, notice that the next step in my undo column is to subtract 2. So if I take that step, I've got 3x equals 33. And then my final step is to divide by 3. So I'll see here that my solution is x equals 11. Let's think about what's going to happen over here for number 2. Number 2, I notice that the structure is pretty much exactly the same, right? The only thing that's a little bit different is that instead of just a plus 2, I've got a plus 2y. I don't know what y is, so therefore I don't know what 2 times y is. I just know it's a thing that I added on to x. Now, if I think about the do and undo column, really the only thing I'd be undoing here is taking away 2y. Everything else is still fundamentally the same, right? So I'm going to open this up by multiplying everything in the equation by 5. It's going to cancel with the division by 5, and that's going to ultimately tell me that I've got 3x plus 2y is equal to 35. Now, on my next step, I'm going to have to think about how to get that 2y off of 3x. The opposite of gaining 2y to it is losing it. So I subtract it over to the other side. I've got 3x in this case is now equal to 35 minus 2y. And then my last move is to divide everything by 3. What you'll notice here is that you could maybe simplify some of the problem. If you're looking at 35 minus 2y all divided by 3, you might be able to take, say, 3 and divide it into 35. No, I take that back. That won't quite work, will it? You need like a 33 or a 36. So yeah, that's about as good as it's going to get there. Until someone tells us what y is and we substitute it in, we're never going to be able to pin down the exact value of x. But as a solution to a literal equation, that's actually just fine the way it is. There's nothing wrong with that at all. Let's do something similar here for like 3 and 4. I've got the do column, and I've got the undo. I'm going to focus on the side of the equation that's got the variable here. And this strategy kind of really only works when you got variables on one side, right? It's a little harder to do when they're everywhere. First, I start with x, but then the next thing that I do appears to be that I'm multiplying it by 4. And then the next thing I do is I take that 4x and I divide it by 3. And then the last thing I do is that I subtract a 5. What I'm now going to do, going backwards, is the total opposite, right? So if the last thing I did was subtract by 5 to create this thing, I need to add 5 to start uncreating it. And then if I divided by 3 to get the next step, I now have to do times 3. And if I multiplied x by 4 in the beginning, now I've got to divide by 4, and that's ultimately going to tell me what x is equal to. So I'm going to follow the process, right? I'm going to start here by adding 5 to both sides. I got to keep this balanced, right? Kind of like the hanger diagram. You want things to maintain that balance. If you do it to only one side, it messes everything up along the way. So I've got 4x divided by 3 equals 16. Now I need to multiply both sides by 3. And what I'm going to notice is that that 3 divided by 3 cancels out. So now I'm left with 4x equals, I believe, 48. So now my final steps to divide the 4 off of that. And now I've got x equals 12. And that's my final answer. I'm going to do pretty much the same thing over here for number 4. It's just that instead of, say, taking away 5, I'm now taking away 5y, which means eventually instead of the opposite of just plus 5, I'm going to do the opposite of plus 5y. So even though I don't know the value of that variable, it doesn't really matter, right? My procedure, my process, my logic behind what I'm doing and when I'm doing it, it still fundamentally remains the same. Now, what maybe might get a little interesting over here is that when I take the step of multiplying both sides by 3, I might have to do some distribution over here because I'm doing 3 times 11, and I'm also doing 3 times 5y. So on the left, I'll have 4x, but on the right, I'll have 33 plus 15y. And then my last step here is going to be to divide both sides by 4. So I kind of create this big, ugly mathematical expression, but x is on its own. And I can say that x is equal to a bunch of stuff that's going to happen over here to y. And as soon as someone tells me what y is, I'll know automatically what x is. I just plug it in and simplify. That's pretty much the process. That's really all we're doing with those literal equations. So as you're working through that algebraic approach where you're thinking like step by step, what is it that I'm doing? How am I undoing things? It's a good way to kind of look at it, right? Let's maybe go from there and do maybe one more. Let's do number 7 here. I like this one. This one's got a lot going on in the process. Number 5 is also a good problem. That 2/5 multiplying onto things kind of complicates it. But I think what I'll do is I'll save that as a warm-up for when I come back after the field trip, and we'll kind of take a look at that all together. Be a good warm-up for me, too. Fractions like that can be a bit of a doozy. If I'm trying to solve number 7, I could definitely do this one with a hanger diagram the more I look at it. But what I might want to do is sort of distribute this too, just to get that step out of the way, right? If I do 2 times 3x, I'm going to have 6 x's. If I do 2 times 4, I'm going to have plus 8 with it. And then it's going to be equal over here on the right-hand side to 4x and plus 12. So if you wanted to think through this with like a hanger diagram, what you're going to notice is that you've got like 6 blocks of x on the left-hand side. Then you've got 8 little unit blocks. 1, 2, 3, 1, 2, 3. You got 1, 1, 1, 1, 1, 1, 1, 1, right? That is perfectly balanced over here on the other side with 4 x blocks and then 12 unit blocks, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? It's not a very good picture because I'm drawing with a tablet. It's not easy to do with this guy, but they're maintaining a perfect balance. They're equal in weight. What I'm trying to do is sort of work backwards to understand, okay, well, what on earth was the original value of x in this context? Now, if I start by focusing on the unit blocks, I've got 8 of them on the left-hand side. I've got 11 of them on the right. If those are perfectly balancing each other out, then that means 8 of those 11 is balancing 8 of them on the left. So if I take that away from both sides of the hanger diagram, I'm sorry, that should be 12 blocks, isn't it? Whoops. There we go. If I take away 8 of them from both sides of the hanger, I'll still be maintaining an equal weight balance. So now I'm at 6x is equal to 4x, right? Now, what I can think about here, well, 4x plus 4, there we go. What I can think about from here is the x blocks. Well, I got 4x blocks on the right. That must be perfectly balancing with 4x blocks on the left. So I can sort of take those away from both sides of the diagram and still be maintaining a balance, right? So that means I've got two x blocks that are somehow balancing with 4 unit blocks. So if I'm thinking about how much each x blocks weighs, it must turn out that each x blocks weighs 2 unit blocks. See how that logic's kind of proceeding from that visual setup, but also kind of like algebraically? You'll notice here that it's sort of an analog for moving the constants to one side of the equation and the variables to the other. Anytime I'm working with that, I could think in terms of a visual aid or diagram, but I could also kind of think of it that way. Move the variables to one side, move the constants to the other. It'll show up here over on the next side for part 8, where after you do that distribution step, you might not necessarily be moving all the variables to one side and all the constants to the other, primarily because there aren't really any constants at all anymore, right? There's all variable terms. But think of it this way. If like 6x and 4x are one type of variable block, and 8y and 12y are a different kind of variable block, you can still maintain the balance, or you can still think in terms of moving the y variables to the right and moving the x variables off to the left. That thinking still works. So eventually what you'll see here is that you got 2x is equal to 4y, and then the last thing you can do is divide 2x by 2 and 4y by 2, and then you figured out that each x blocks weighs 2 y blocks. So the structure is really the same, right? With literal equations, you got some extra variables, but the procedure is really not all that different. So what we're really doing here is just continuing the practice, right? We're just continuing getting comfortable with these different representations across the board, whether they're literal, whether they're algebraic, what's the structure between them, and how do we emphasize and use that, right? To close things out, I want to hit maybe one last one. That's a full literal equation. There's not a single number anywhere in this problem. My goal is to try and solve for x, right? Get x completely on its own. This is a bit more complicated, right? And as you graduate on into harder and harder math classes in high school and beyond, you're going to be dealing with more and more formulas where they're going to look a lot more like this. There's going to be hardly any numbers at all. So getting comfortable working with them early and utilizing that algebraic structure, it's a really important skill. Now, our goal here is to try and solve for x. Before we undo this thing, right? Before I try and cancel everything out and think about like what I'm doing and when I'm doing it, let's maybe slow down a bit and really focus on the structure of how this thing got created on the left-hand side of the equal sign in the first place. So if I'm thinking about like a do-undo table, right? Here's what's happening to x. First, there's just x. But then if you look at the left-hand side here, you multiplied it by a. Once you had ax, then you added b to it. And once you had ax plus b, then you divided by c. And then the last thing you did is you subtracted by d. And then you have the equation, and we're trying to undo it, right? So going down the column on the right, notice you got to undo the last thing you did on the left, and you got to use the opposite operation. So instead of subtracting, you add it. And it's going to cancel some things out. Then you multiply by c, and then you subtract by b, and then you finally divide by a. So let's take a look and see what that's going to look like. If I've got my equation, and I want to add d to both sides of the problem, it's going to cancel out on the left-hand side. And this is now going to look something more like ax plus b over c is equal to e plus d on the right. I want to take a moment to kind of diverge here and talk a little bit about what we mean by cancel out. If I cancel out like positive something with negative something, if I do like positive 3 and negative 3, or positive 5 and negative 5, when I add those together, what number do I get there? I get a 0, right? So when I'm talking about undoing addition and subtraction, I'm trying to like choose just the right things so that if I add them together, I get nothing, right? It comes out as a big fat 0. which means I don't even have to write it anymore in the problem because to do plus zero with something is to do nothing at all. So that's what we mean there when we say cancel out. I wanted to kind of pause there and maybe hit that vocab term. Now, the next thing I have to do is multiply by c. We're going to notice here on the left-hand side that c divided by c is going to cancel out. And that's going to leave ax plus b is equal to c times e plus d. But I could distribute that, so I might see something like ce plus dc. Same thing. I want to talk over here real fast about what we mean by cancel out when we're talking about multiplication and division. If I take something and I divide it by itself, or if I take like a fraction 1 over 2 and I multiply it by 2, what do I get? I don't get nothing, right? I get a different number entirely. I get a 1. And if you think about what 1 times anything does, it doesn't do anything at all. It just leaves behind the thing that you were multiplying onto it, right? So that's kind of interesting that opposites in addition add or subtract to be 0, but opposites in multiplication they multiply or divide to be equal to 1. So those are very different things, but we never really kind of slow down to focus on that, right? We kind of just go right into it with solving and sort of forget that that's a truth. Now, as I go from here, I'm going to think about my next step where I'm subtracting by b. So now I've got AX is equal to CE plus DC minus B, this whole awful mess on the right-hand side, cancels out to form a 0 on the left, and that's why it disappeared. And then my last thing to solve for X is that I got to divide both sides by A, right? So what I'm finally seeing is that CE plus DC minus B all divided by A, that's the value of X. So if someone tells me what A, B, C, D, and E are, then I could finally figure out my value for X, but not until they tell me, right? So I got to know 5 more pieces of information before I can figure out the 6th. What's the value of X? That's very often the case with literal equations. So as you're working through these equations and you're thinking about like how to do and undo, how to invert something and its opposite, one thing that I want you to kind of start mulling over is like, well, what's the opposite of addition and what does it leave behind? What's the opposite of multiplication and what does that leave behind when I say the term cancel out? That's kind of a more important concept as you go further in math, especially as you introduce more sophisticated operations like square rooting or logarithms or exponents. It gets more and more tricky. We'll maybe save this one as a warm-up. This one I wanted to throw in there as a ready for more, just to kind of continue playing with this notion, but I think we got plenty to chew on for right now on the ready, set, go as it is. We'll revisit this once I'm in the room together, and we can sort of handle this all as a big crew and sort of reason through that, because that square root there is kind of a little more interesting, right? Now, as we close out for today, the idea of solving as a series of inverted steps for a forwards process, that part's really not that new, right? We've been practicing that now for a few lessons. I wanted to kind of add some more terminology, some more mathematical thinking about why these things cancel each other out and make it easier as we go. There's kind of 2 major things that we've seen. We've seen properties of addition and properties of multiplication where we're trying to cancel things, right? The big idea is that if you have something plus itself, it gets twice as large, right? But what if you do something minus itself? Or if you have a negative something and you do plus it in the positive sense, well, that forms nothing, right? It forms a 0. That 0 is what we call the additive identity. That's a fancy way of saying that if you take something and add 0 to it, it does nothing. It does nothing because by definition, it's the opposite of, rather, it's the result of doing something and then its opposite, right? It cancels. There's something similar with multiplication. In multiplication, we don't say that there's an additive identity, we say there's a multiplicative identity. And it's a different number, right? You have to multiply something by 1 to not do anything. Because if you multiply something by 0, you get something very different. You get 0. Now, the multiplicative inverse is the opposite of what you started with. So if I have A, or if I multiply something by A and I want to undo it, I need to divide it. Or multiply it by the fraction 1 over that thing. Similarly, if I have like 1 divided by A and I want to undo division by A, I multiply everything by A and they cancel each other out, but they leave behind a 1. That's the multiplicative identity. The other two properties that you'll see here on the right are kind of more like facts. If you think about this one called the commutative property, what this says is that if you do one operation on two terms, it doesn't matter the order you do it. 3 plus 5 is the same thing as 5 plus 3. And same thing for multiplication. 3 times 5, same thing as 5 times 3. Doesn't matter. It also works if you have three terms. So if you do b plus c and then you do a plus that, that would ultimately be the same thing as doing a plus b first and then plus c at the end. It also works with multiplication too. If you do a times the quantity b times c first, it's the same thing as doing a times b first and then multiplying by c. So you can kind of shuffle the order in which you're doing this, and it doesn't hurt a thing. And that's ultimately why you can kind of take that in further context and do like multiple multiplication steps and cancel out any one of them first without really disrupting the flow of solving. So these are nice to know. These aren't as crucially important as the actual procedure, but they're nice to kind of think about as to why this stuff works in a more mathematical case. So that's our lesson for today. You guys should have a little bit of time to start on the Ready, Set, Go for 4.3 in the notes. So I want you to go ahead and give that a spin. You'll notice most of what we're doing is working with equations, literal or algebraic. We're thinking opposite operations to cancel. But there's also a little bit of inequalities work, and there's some more stuff from some of the old stuff from our last unit. So if you've got some questions, definitely hold on to them. I'm going to be back in the building on Friday or Monday for you guys. I'll be more than happy to kind of work through some of the tougher examples here, and we'll kind of recap and review before we dive into some of the more new stuff. Apart from that, though, I hope you guys have a great rest of your day. I'll see you guys again soon. Enjoy the weekend.